Okay. All right. So before we discuss conditional probability and independence, I would like to address some of the factors on discrete sample spaces. Okay. So first of all, we learned to use mathematical model to formulate a random experiment. Okay, so such mathematical models consists of sample space X, sigma algebra F, and a probability function P on F. For a random experiment, okay, it's called a probability space. Okay, or a probabilistic model, but I prefer to use probability space to describe such a mathematical model for a random experiment. Okay, so so if we want to investigate a random experiment, we have to establish first a sample space for this experiment, and then we will select a proper collection of events of interest we call a sigma algebra, which satisfies some logical structure. Okay, and then a probability function which assigns a probability to a member in this sigma algebra. That is to assign a probability to each event of interest. Okay, so all right, now if the sample space, so if the sample space X consists of countably many outcomes, all right, says omega 1, omega 2, etc. So we can count the outcomes in the sample space. Then X is called a discrete sample space. Right? So this is what we encountered most of the examples in chapter 2. Okay. And And in this case, right? So in this case, the power set of X is usually selected as the sigma algebra, i.e. F is selected to the power set of the sum space. All right, and the event which consists of only one outcome in the sample space is called an atomic event. Okay? So that is the smallest event other than the empty set. As we know, the empty set is an event. We call the null event. Just like the sample space is an event, we call the total event. So an event which consists of only one outcome is called an atomic event. Okay, and then we can write down a proposition. Okay, for a discrete sample space with sigma algebra f equal to 2 to the x, a probability function P on F is uniquely determined by its values at atomic event. Okay. And furthermore, PE is equal to the sum of the omega and the proof is simple. By things is a countable set. Any any event E in F okay, so any event in F which is just a subset of X is also countable. Okay, and E can be expressed as the disjoint union of the atomic events for all the outcomes in the event. Because all these atomic events are disjoint. Why? Because they are different outcomes. So the intersection is empty. Okay? And it's a union, of course. Okay? So E can be expressed, which is a disjoint union of countable the many atomic events. Okay? Right? And so by axiom number 3, countable additivity, or I just say by the countable additivity which is axiom number 3 of a probability function P, we have probability of E is equal to the sum of the probability of the atomic event. And so the probability measure is uniquely defined by its value on atomic events. Okay, so to describe, so this proposition is quite useful. If to describe a probability function, it is sufficient that you describe the value of the probability function at atomic events. Questions? Okay, so in chapter 2, section 5, we consider running experiments such that all outcomes are equally likely to occur. Okay, and so we assign that so in section 2.5, we consider random experiments whose outcomes are equally likely to occur i.e. the probability of an atomic event is equal to 1 over the, okay. for X, the sum space must be a finite set. Because that in the recommended exercise number 2, all right, there is one exercise which shows that if the sample space is infinite, then the outcomes cannot be equally likely to occur, right? If you solve that problem, okay? So to have outcomes to be equally likely to occur, the sum space must be finite. Okay, must be finite. All right, and so that in section 2.5, actually we require that the probability function has values at atomic events. Okay, every atomic, which is 1 over the size of the sum space. And this assignment will determine the probability function uniquely, okay, as the proposition says. Okay. Okay. And this proposition is also valid for arbitrary probability functions, even for outcomes, for random experiments whose outcomes are not equally likely, as you have solved a problem in quiz number 2 last night. Okay? Any questions? Okay, so I have introduced quite a few terminologies like discrete, right? Sample space, describe atomic events. Okay, so there are some basic terms that I will use quite often. Okay, so now the next section is about conditional probabilities. All right. Conditional probabilities and independence, these two basic concepts is very fundamental in the theory of probability. Okay, and they are quite distinct from other branches of mathematics like linear algebra, differential equations, a lot of things. Okay, so I would like you to grasp the basic principles of these two concepts. All right, so these two concepts will be introduced in chapter number 3. So if you have any question, raise your hands as quick as possible. Okay, because that is so basic. If you cannot grasp the basic spirits or understanding of these two concepts, you will get into trouble to learn the rest of the subject in the semester. Okay. All right. So now I define conditional probability as follows. So the conditional probability that event E occurs given that event F has occurred. Right? So the condition is that given. So given that event F, so we know event F has occurred already, and then we want to know, under this condition, we want to know the conditional probability that event E occur. And the notation is here. Okay, so the vertical line says that given F, okay? So this is called the conditional probability of event E to occur given that event F has occurred. And it's defined the following. Okay, so this concept is defined. It's by definition. Okay, it's created by definition. In Venn diagram, is that this is F, okay, and this is E. Okay, and so given that event F has occurred, event F has occurred means that one of the outcomes in this set F appears, okay, as a result of the random experiment. Okay, that means F has occurred means that one of the member, right, or one of the outcomes in F appears as a result of the random experiment. And then given this event, and we say that E occurs. So now, under F, E occurs. That means that one of the outcomes in this part appears as the result of the random experiments. Okay? So, and here, this is E intersect with F. Okay, so that this is just the relative, the ratio that the probability that this intersected event divided by the probability that the event F. Okay, and because we put the probability of F in the denominator, so it is required the probability of F is greater than 0. Okay? So this is crucial. We can have this quantity only if that event F occurs with positive probability. Okay. So okay, and so this is important. So I will give it an equation number 3.1. Now, for further discussion, when the probability of event F is 0, okay, so we also define conditional probability, okay? So we define that to be what? To be the probability of E. Okay, that just by definition only. Okay. Okay, I forgot to and the intuition is here. If the sample space X is finite and the outcomes are equally likely to occur, then the conditional probability of event E given event F is equal to okay. And as I mentioned, P is the counting measure. Is a counting probability measure. And the conditional probability comes to okay. Okay, so the conditional probability is the ratio of the size of the intersection of E and F to the size of F. Okay, so it becomes to the size of the intersection divided by the size of F. Okay. Okay, so let's consider example 3.2.d in the textbook. The random experiment is to linearly arrange R red balls and B blue balls in n positions. And the n is less than or equal to R plus B. Okay, So we have R red balls and B blue balls. Okay, so together we have B plus R balls, and we want to linearly arrange this ball in n positions. Okay, and n may be less than R plus B. Okay, so to have a probability space to model this random experiment, we treat. So we will identify the red balls as one to be up to R, and the B blue balls as B1, B2 up to BB. Okay. So we treat every ball as individual balls, okay, and identify them with a different index. All right, so okay, with that, so the sample space it's the set of all linear arrangement of this R plus B balls in n positions. Okay, and the size of X is what? Is that because we have position number 1, 2, n, so that for the first position, they are R plus B choices. So we have R plus B choices for the first position. And for the second position, we have R plus B minus 1 up to R plus B minus n minus 1. Okay, so that is the choice of the last position. Okay, and this is R plus B factorial divided by R plus B minus n factorial. Okay, so that is the linear arrangement. And of course that because now X is a finite set, and so it's a discrete sample space, the single algebra is selected to be the power set of X. And the probability function here, by the nature of the random experiment, because we arrange that, okay, without any preference, so that the P is the counting probability measure, because that each outcomes are equally likely to occur. So the counting probability measure. Okay. to reflect the intuition that outcomes are equally likely to occur. Right. So that is the major. So we have the sample space, sigma algebra, and probability function. Okay, so now event F. What is the event F? Event F is the K of the chosen n balls are blue. Okay? Right, so F is the event that K of the chosen n balls, because that we choose n balls to put into n positions. Okay? And K of the chosen n balls are blue. So what is the size of F? First of all, you select, because that K of the n balls are blue, but we have B blue balls. So first of all, you may think about that this K blue balls are selected from the B blue balls, and the rest n minus 6 balls are red balls. They are selected from our red balls. Okay. Then once that you have n factorial. Okay, because now you select K out from the B blue balls, select n minus K balls from the R red balls. Okay, so now you have n balls at hand. Okay, and then you will make a linear arrangement. So you have n factorial because it's a permutation. All right. The other event E, the first ball chosen is blue. Okay? So the first ball chosen is blue. And so then E intersects F, okay, has the size. So what is E intersect F? E intersect F is that in the linear arrangement, they are exactly K blue balls. And the first ball here is blue. Okay? So now, so the size is that the first position should be one of the B blue balls. Okay, so you have B select 1. And then the rest you select from the rest of the blue balls you select K minus 1s. Okay. And then you must have n minus K red balls. So you select this n minus K red balls from R red balls here. And finally, the rest n minus 1 balls. Okay? K minus 1 plus n minus K is equal to n minus 1. You will make arrangement in raised -1 positions. Okay, so you have these numbers. Okay, so now the probability, the conditional probability that the first ball chosen is blue, given that there are exactly k balls in the linear arrangement. Okay. All right, and as we demonstrate here, if the probability function is the counting probability measure, then we know this is E intersects F divided by the size of the E intersect F divided by the size of F. Okay, and so you put them there. Okay, so the result would be K over N. Okay. Then denominator B1. Oh, yeah, sorry. Okay. Thank you. I have to upside down. Okay. Thank you so much. So this is B. Okay. Yeah, that's why. Yeah, this is N here. Okay, so we can cancel and yeah. Okay, 1. Okay, sorry. Thank you. Questions? Okay, now from this formula, the definition of conditional probability when the probability of the given function, the given event f is has positive probability, as well as here. Together, we can rewrite okay, and we call this formula 3.1 prime. Okay. So by 3.1 and 3.1 prime. Okay, so we can have the probability of the intersected event E and F is equal to probability of times probability of E given F. Right, this is called equation 3.2. This equation is useful if we want to compute this probability. Because in some problems that it is quite straightforward to find the conditional probability. Okay. Okay, so let's take an example. Oh, okay. (3.2.f). Okay, so in an there are 8 red balls, each with weight R, and 4 white balls, okay, each with weight W. Okay? Right? So the random experiment is to draw 2 balls from the arm without replacement. Okay, so that so they are an arm, okay, and okay, right. So inside arm, there are 8. Okay, so there are 8 red balls, each with weight R. In my drawing, red ball is lighter than white balls. White ball is bigger, something like that. Or okay, and so so the random experiment is to draw 2 balls. All right, so you can't look at the entire, just randomly draw, right? 2 balls, 1 by 1, okay, without replacement. Okay, so you first of all you select 1, and then second. All right, and there is one intuition, or sometimes we call a priori information. All right. A priori information. I use this word in the statement in a problem in quiz number 2. But so sometimes we call intuition, but sometimes we say a priori information. Say that the probability, okay, that a ball is the next to be drawn is equal to the weight of the ball divided by the total weight of all balls. okay, currently in the urn. Okay, so for example, if you want to draw the first ball, right? With high probability, you will touch bigger ball, right? With high probability, and then you pick up one. Okay, so you take one out of it, right? And for the second ball, when you draw the second ball, again, that the probability or the likelihood that a ball will be drawn were equal to, just the relative weight. Okay, so that is an intuition. Okay, I think that we may all agree, right, for that situation. Okay, so this is a random experiment, and we have this an intuition. So maybe I will say an intuition. Okay, be that. Okay, so let's take a brief break. Okay, for 5 minutes. Okay, before we solve this problem. Okay, I'm sorry. Actually, I have to give proof for this formula, especially when the probability of event F is equal to 0. Okay, so I give proof here. So thank you. I forgot to ask your name for remind me to give a proof. Okay. Okay, so the basic thing is that when this probability is 0, then this probability must be 0. Okay. So no matter what is this, okay, this also more automatically true. Okay, all right. So so we continue so our job is to establish a probability space or a probabilistic model for this random experiment, such that it will fulfill our intuition here. Okay. All right, and to reflect our intuition. Okay, so of course, right? So x, what is x? So x is the set of all ordered pair or ordered pairs of distinct balls and the size is P2, so which is (132) possible outcomes, because we have 12 balls in the arm initially. Okay, so the first draw, okay, is one of the 12 balls. Okay, and after the first draw, there are 11 balls left in the arm, so that one of the 11 balls will be drawn. Okay, for the second time. All right, so this is that. So x is no problem with that, and because x is discrete, and so usually the schematic algebra is the power state. Now the problem would be the probability function, because that intuition is about the probability function, the description of that. Okay, so, and from our proposition 3.1.8, okay, to uniquely describe the probability function reflecting this intuition is that we have to assign probability to atomic events. That means that we have to assign probabilities to how many atomic events do we have? We have 132 atomic events. Okay, so we have to do that systematically. Okay, so to do that, we will describe 4 kinds of events. Okay, so E sub 1, grade I, the event that the first ball drawn is rayed. Ball I. So I is from 1 to 8 because we have 8 red balls. Okay, and E1 white J is the event that the first ball drawn is white ball J, and J is the index of J is from 1 to 4 because we have 4 white balls. And it is usually useful to treat each ball, even though they have the same color. We treat each red ball distinct balls, so we give distinct indices. And that's the same for the 4 white balls. So we have the first white ball, second and third and the fourth, etc. Anyway, so that is the okay, and red I is that the event that the second ball drawn is red ball I. Okay, E sub 2 white J is the event that the second drawn is white J. Okay. Right? Now we can describe atomic events by using these 4 kinds of events. Okay, so then red I and white J, for example. So the first ball drawn is the red I. The second ball drawn is white J. All right. So that is E1 red I intersect E2 white J. Okay. And similarly, you can have white J, red I, intersects. Okay. there are other two kind of atomic event. So say with I prime, E1 with I intersect E2 with I prime, and white J prime, E1 white J intersects E2 white J prime. Okay, so it is sufficient to find the probability of each of these kind of atomic events. All right, and as here, because each atomic event can be expressed as intersection of two of the four kinds of events there. Okay. And we can see that so to reflect our intuition, the probability function P has to have the following properties. First of all, probability of E1 raised to I. Okay, so to draw the first draw, right? The first ball drawn is raised I. So what is the probability? Okay, the total weight before the first draw is it's HR plus 4W, because each red ball has weight R, each white ball has weight W. Okay, so this is the total weight, and red I will be drawn as the first ball drawn is here is R, because each red ball has weight R. Okay, and so subsequently, white J X W it's R plus 4W. Okay, so that is about the drawing. How about probabilities of E2 and the red I? Okay, well, this is so that this is depends on the first ball, the first draw. Okay, so the second is that the second draw with I prime given the first is red I. Okay, so when the first draw is red I, so one of the red ball has been drawn, right? So in the womb, before the second draw, there are 4 white balls and 7 red balls. So the total weight is 7 red ball plus 4 white ball. And then red I prime will be drawn as the second ball, so that this is R here. Right? So given this event for the second draw, the probability, so we have this conditional probability. J given. Okay, so that is 7R plus 4W and W here. There are other two possibilities that if the first ball drawn is white, so there are 3 white ball and 8 red ball left. So 8R plus 3 white. And then the second ball drawn is red I will be R. And finally, okay, but if the first ball drawn is red, so we have, oh, sorry, this already counted. White J prime, white J, okay. So we have 8R plus 3W and W here. Okay, so these two are from our intuition. And now we can apply equation 3.3 to compute the probability of atomic events. Okay, so now, so this says that probability of red I, white J. Okay, it's here. So this is the probability of event 1 red I. Probability of E2 white J given event 1 red I. And so this is R, 8R plus 4W times here W 7R plus 4W. Okay, so this is from here. And this is from here. All right, similarly, we can write down the other 3 kind of atomic events. So probability white J, red I, probability that E1 is white J times E2 is red I given E1 is white J. So this is W, 8R plus 4W times 8R plus 3W and R here. Okay. Similarly, red I prime, probability E1, red I times probability E2, red I prime given E1, red I. So that it's R, 8R plus 4W times 7R plus 4W R. And finally, white J prime E1 white J times probability E2 white J prime given E1 white J, which is equal to 8R plus 4W, and the W divided by times 8R plus 3W. Okay, so you can see that the outcomes are not equally likely to occur. Okay, they are not equally likely to occur. Okay, and so this intuition gives us a unique probability function, and this probability function, when we describe that it is sufficient to give probability to atomic events, and we have 4 kinds of atomic events, and their probability has been assigned here. Okay, and so we have done. So our goal is achieved. Now, questions? Okay, and now, so this is an application of the formula 3.2. So a generalization. So as a generalization, we have the multiplication rule, which says that if you want to consider the intersection of n events and to find the probability of this intersection. All right, then you can do it. First of all, you find the probability of event number 1, and then you find the conditional probability of event number 2 given event number 1. And times the probability that event number 3 given that event number 1 and event number 2 has occurred simultaneously. Right? And up to probability of En given E1 intersect E2 okay? And the proof as an exercise. The hint is by induction on N. Okay. Okay, so multiplication rule actually is a generalization of the identity 3.2. All right? So this formula is useful when the intuition gives you the idea to compute conditional probability, right? Okay, and so so there are quite a few examples in section 3.2 for you to learn in the textbook to apply the multiplication rule. Okay? Right? And for this section, I would like to introduce Bayes' formula. Okay. All right. In many situations, okay, so in many situations, it is difficult to compute the probability of an event. Okay? Directly. But it becomes straightforward to compute it once we know whether or not some second event F has occurred. Okay. Right? So that is a situation that's difficult to compute the probability of an event directly. Difficult. But if you know another information, you know another event, suppose you are given an event has occurred, right? Or an event has not occurred, then it may become straightforward to compute the conditional probability of this event. In this situation, then a formula called Bayes formula will be useful. So let me address it. So in Venn diagram, this is the event E, and it's hard to compute its probability directly. Now, suppose that, so this is our sample space, okay? And the sample space can be decomposed into two parts. Right? If we know F, so this is F, and then this is F complement. Okay? Right? So that so in here we know that X is equal to F disjoint union of F complement, right? Okay, and so E can be divided into two parts. So E intersect, E is equal to E intersect S, because X is the total event, right? And now E intersect this union. disjoint union here. Now, by the distributive laws of intersection to union, you are required to prove that, right? For countable many intersections. In the quiz number 2, so this is the disjoint union of, so this is E intersect F, disjoint union, E intersect F complement. Okay, so this part is E intersects F complement, and this part is E intersect F. Okay? Now, so the probability of E, okay, is equal to the probability of E intersect F disjoint union E intersect F complement. Right? Because E is equal to the disjoint union of these two parts. So we partition E into two parts. Now, by the finite additivity, that is proposition 2.3 okay, of A. Okay, I forgot it. Anyway, so I will say, so this is the sum of by finite additivity of P. Okay? Because this is disjoint union. All right, and we apply formula 3.2 here. So this is P, F, probability of E given F, plus probability of F complement, probability of E given F complement. So PE is equal to this one. This is 3.3. So this is called the decomposition formula. Okay? Right? So this is called the decomposition formula because we decompose event E into two disjoint parts by using another event F. Okay, so and so that to compute the probability of event E is equal to compute the conditional probability of event E given F, event F has occurred, and the conditional probability of event E given event F does not occur, hasn't occurred before. Okay, and we know that the probability of F and the probability of F complement. It seems complicated, right? Because to compute it, we have to know 4 probabilities before we use this decomposition formula. But because this is so difficult, and they are easy, right? It's easy to compute these 4 quantities. Well, so the price is very cheap. Okay, and you can really compute. So the decomposition formula is quite useful. Okay. All right, and so So now I will give an example, and this I can't finish this example today. All right. So I will describe the example. Okay. All right. So okay. So random experiment. They are n cards. Okay. Indexed by 1 by integers in 1 to n. Right, so they are n cards indexed by integer in a deck. Okay? And this card is shuffled. And then turn over 1 at a time. Right, so you have n cards, and each card is indexed by integers. So you can say card number 1, card number 2, up to card number n. Okay, so it's a deck of cards. You write the integers, the index on the card, 1, 2, 3, 4, 5, n. And you shuffle it. Okay? You shuffle it. After you shuffle the deck, then you will turn over 1 by 1. Okay? Because you have n card, right? So you turn over 1 by 1, 1 by 1. Okay? Turn over 1 by 1. Now, so there is a player. Now at each time, a player can guess the next card to be turned over will be card number 1, will be card 1. If it is, then the player wins. In addition, the player is said to win if card number 1, if card 1 has not yet appear when only one card remains and no guess has yet been made. Okay, so again is that I have said that we have a deck of cards and we shuffle it. All right, and after shuffling that, we will turn the card one by one. Before we turn one card, the player can make a guess. But the player always guesses that the next card to be turned over is card number 1. Okay, because he or she just like the card number 1. Okay, so before turn one card over, the player will decide to guess whether to guess or not. If he or she decide not to get, then just turn it over. Okay, and if no guess and if card number 1 is turned over, then of course the player will lose the game, of course, because the player does not make any guess. Okay. And so the player may not make any guess, right? So no guess at all. And after M-1's card has been turned over, there's one card left, right? Remain. All right, and if the condition is that if card number 1 has not yet appeared, all right, when only one card remains, then of course the remaining card should be card number 1. Should be card number 1. Okay, and so of course the player will say, okay, next one is number 1 for sure, right? So in this situation, the player will win, of course. So that is the idea. Now, the player need to have a strategy to make a guess. So there are quite so many different strategies to make a guess. Okay? So what is the goal? So this is the random experiment. Do you have any question about this random experiment? How the game goes on? Any questions? All right. So if no question, oh, okay, I think I see it. So what is the best strategy of making a guess to win? Okay. So that the problem is, what is the best strategies? Because that the player have a choice to make a guess or not at any time a card to be turned over, right? So there are so many strategies. So what is the best strategy of making a guess to win? Okay, because the player can only make one guess, right? Only one guess. But he or she can wait. Okay, he or she can wait. Okay? So maybe you will choose a strategy that, well, I will make the guess at the first time. That is one strategy, right? The other strategy is that, well, I will not make any guess until the last card remains. This is another possibility, right? So there are so many different strategies. Okay. And actually, some people I study this problem and find that a stronger result can be established. So actually, by induction. So actually, a stronger result can be proven by induction. That so for a deck of n cards, indexed by integers in 1 of n, the probability of winning is 1 over n, no matter which strategy, right? No matter which strategy is chosen. Okay. So we will prove that actually, no matter what kind of strategy you choose, the winning probability will be the same, all the same. And this winning probability is 1 over n. It's 1 over n. It's a surprise result, right? It's a surprise result. Of course, as a first step, we have to establish a probability space. So Sn, Fn, Pn for the random experiment with n cards. And this is our first example that we have to deal with infinitely many probability space, because the probability space will depend on the number of cards in the deck. And as we say, the strong result can be proved by induction on what? On n, on the number of cards in a deck. Okay, so, all right, so to solve this problem, you will see, for different n, we will have different probability space. And we will consider all of them to be able to solve this problem. That is the complexity of this problem. Okay? It's a complex problem. Any questions? Because I have to stop here. Okay? Okay, so I will see you on Thursday.